Well, hi everyone. Today I'm going to be talking about the use of the built-in MATLAB functions ode45 and nlinfit, particularly as they apply to the modeling of the cooling fin. And the one thing that you should know, or one of the things that you should know about cooling fins, and that you may already know about them based on your Transport 2 class, is that there are some pretty well knowable equations that describe the temperature profile, steady state temperature profile of different geometries of cooling fins. So the ones that we have are all cylindrical, and I'll show you one of the analytical solutions for a cooling fin. As I said, they're pretty well knowable, and this is just on a Wikipedia page. You can find more in-depth information in some of your textbooks and most of your heat transfer textbooks. But basically the main thing to note is that there are different assumptions of cooling fins. So you can have ones that convect from the tip, the end portion of the cooling fin, adiabatic tips. The assumption that you will likely make for this experiment is that the cooling fin is infinitely long. And what this means is that you can basically say that the temperature at the end of the cooling fin is always equal to the adiabatic, or sorry, the ambient temperature. So this simplifies the equation, and it acts as basically a boundary condition for you to solve the differential equation. Here's the analytical solution to the infinitely long fin case, where this theta x is equal to the temperature at position x minus the temperature of the ambient, and the theta sub b is the temperature of the base of the fin, which is for our case where the steam is. So we tend to think of that as a steam temperature, but that is kind of an assumption in and of itself. Won't actually be the temperature of the steam. You might look into that assumption, but that theta sub b will think to be the temperature of the steam minus the temperature of the ambient. And so it's multiplied times this exponential term scaled by a distance x, and it includes, as you can see, the convective heat transfer coefficient h. And you look at this equation, and there are a couple of things to note about it that are particularly relevant to our experimental case. One thing that I kind of alluded to previously was that this is a steady state temperature profile. So when you do the experiment, you're going to be tracking temperature versus time, and you may try different steam pressures. I'm not sure exactly what all you're going to be doing for the experiment, but you'll be tracking this steam temperature versus time. You'll be getting like this nice first order response, or you should be, of temperature versus time at all your different positions. And so you'll be having all this data of temperature versus time, but this is only good for the case at the end time where the temperatures are constant. So it's pretty limited in what you can apply this case to with respect to all the data you're collecting. So it would be nice if there were some way for us to look at or for us to model the unsteady state, the startup case, and compare that to what we see experimentally. Also, the other thing to note about this is that, as I said, it involves the convective heat transfer coefficient. However, we don't really have a good we have a range that we may expect H to vary between, depending on what the thermal boundary layer looks like and things like that. It's a pretty broad range, and you can look at that in some of your heat transfer textbooks. But we don't have a very good prediction of what H can be. It can be a pretty wide range of values. So we don't know what this is, so we can't just plug and chug this into MATLAB or into Excel or something like that and determine temperatures for all position. But MATLAB can help us, and the two things I'd like to focus on in MATLAB, as I said, is ode45 and nlinfit. ode45 will help us for the case of determining the unsteady state temperature profiles. But to use ode45, we'll need to basically write, before we try to code this into MATLAB, we'll need to write the energy balances, the shell balance, for the fin, and perform a method of lines type solution on it. And you should probably have heard of, probably know method of lines, at least qualitatively. Perhaps you've done some homeworks with it. You should know that from your analysis course. But basically, we'll write the heat conduction equation for the fin, and along with it, if you go up here, you'll see you'll see some of this type of stuff, like looking at the heat transfer at position X plus delta X plus this differential amount of heat convection, heat convection from the surface. The one thing that you'll note about this, that they refer to it as X. Really, we're working with cylindrical fins, so it's probably more accurate to think of it as a Z coordinate. However, the thing you'll know about this is they treat this as a one-dimensional conduction, which, if you think of it, cannot be true, because if we're having convection from the ambient, then, or to the ambient, then what must be happening is that there must be heat transferring radially through the fin. And so that would imply that there should be some partial T, partial R terms in here, that there's a variation, that temperature is a function of R. However, the assumption usually is that the temperature is not a function of R, that the R is small enough, that the radius of the fin is small with respect to the length. So you usually assume that the temperature doesn't depend on R, but still, obviously, convection is must be taken into account. So you're basically saying that the temperature with respect to R is for a given X or Z is everywhere the same, but it's convecting to the ambient. So you'd write that heat balance down. So you'll have terms like this second partial derivative of temperature with respect to Z. You'll have terms like that. You'll have the convection term. Be careful of how you specify your areas. I won't go through exactly how to do this. I mean, that should be something that you can do from, like I said, based on transport 2 and stuff. But what I'm going to focus on is how to work this up in MATLAB. So this is, as I said, referring to the ode45 bit, so I'll go through that first before I go through nlinfit. So now we should see MATLAB here. I've made some kind of this is some temperature and position data that may or may not reflect what you'll see. It should be an estimate of what it will be experimentally. This is just so this is my script file in MATLAB. This is just some like constants that I'll need and stuff. I guess I can show you the ode45 function file first. This is my ode45 function file. This is what I'm using method of lines in. This is what is going to give me that unsteady state temperature profile for each individual position. So basically the idea here is I know depending on when you took this class, you may or may not have gone into detail on ode45 or nlinfit. So I'm just going to kind of show you how this goes. So this is just a bunch of constants right here. This is just a bunch of constants that you may need. I've defined some radiation terms, which you can actually, it's actually interesting. The equations that I just showed you that are kind of well knowable, they take into account convection from the surface, but they don't take into account radiation. So that might be an interesting effect to look at, because radiation is where the points where you have like 200-degree surface temperatures for the fin, there's certainly going to be radiation from that. Although it might be minimal depending on if this emissivity value is a fairly accurate one. You see it's pretty low, so maybe that radiation isn't a big deal, but it could be something that you look into. At any rate, though, what you notice here is that I'm passing in a time vector, a vector which I'll redefine as a temperature vector further down, and this optional argument. So these two are required arguments. This is an optional argument that I've named n. That's just the number of nodes for the method of lines. So I can make it 5, 10, 100, and it will accordingly solve those differential equations inside of this for loop that you see here. Before we get to that, though, boundary conditions. And this is an important one. This is just where you define the thickness of each node, of each basically slice of the fin that you're sectioning up based on your method of lines, number of nodes. This is and these are the two boundary conditions that you'll need, because you'll really need a total of 3 boundary conditions. You'll need the firstly, this one is you'll need 2 boundary conditions with respect to the z position for all time. So the way that we know that is, of course, because we have a second partial derivative of temperature with respect to z, so therefore we need 2 boundary conditions of temperature for at a particular z for all time. So these are our 2. That's the first z, basically z equals 0, is equal to the temperature of the steam, 250. That's about the temperature of a 15 psi steam. And then the final, the temperature at the n node, so that's why I give it the index n, is equal to the ambient temperature. So that's the infinitely long fin case that I, kind of the assumption that I talked about. Okay, so and we'll need to repeat these boundary conditions in our script file, which I'll show you in a bit. So that MATLAB can keep track of boundary conditions and can basically pin down these temperatures at these points and solve the solution accordingly. So now this is where the this is my this is my derivative of temperature with respect to time equation that we build up based on the energy balance that we do. Okay, so this A is just a thermal diffusivity. This is the central difference approximation. Okay, for a second order derivative. Pretty straightforward here. This is just, you know, this is just what you get out after you do the math. This A is out, this thermal diffusivity is multiplied times all of this, as you can see. Pretty straightforward, and that's it. So most of these lines of code that you're seeing is actually just calling out, is nothing more than declaring functions. This is, or sorry, declaring constants. This is the only place where you know, some intensive loop actually happens, where you're actually populating up this time derivative of temperature column vector. So if we go back to the script file, again, constants, they're, you know, more succinct way to do this. You can just make up a vector of constants and then pass that into the function file, but I was lazy and just typed them out, or really copy and pasted them all again, but you can see them here. And as I said, you'll need to redefine your boundary conditions here. So this is your temperature of the steam. I went ahead and the rest of them are going to be, it's initially at the ambient temperature, so all the other temperature nodes besides the z equals 0 node is at 250, or sorry, at the ambient, which is 75. Okay, and so then we define some position vectors that we'll need later on. This is basically more for plotting purposes, so you should be familiar with, like, in MATLAB, whenever you're plotting points or plotting a line, the x and the y vectors need to be of equal lengths. So because I'm always kind of plotting the same type of quantities down here, and this is, yeah, this is z versus temperature. You know, it's just that sometimes they're different lengths, so you need to make sure you have the position vectors matching up with the their correct temperatures. Even though the position vectors don't really change in terms of value or range or anything like that. Alright, so this is where we call, this is where we actually call the ode45 function. You have to name your function file that I just showed you, and this is your function handle. So you call that function, give it your time range. This is in seconds, so this is like an hour. Okay. And this is our initial temperature vector. I don't have any options here, so I just have empty brackets. You have to put those if you don't have any options, and specify things after that. And the thing I specify after it is the n, the number of nodes that I showed you before, and I specify that further up here. I just give it 30s because I assume the fin is 3 feet long, and so each it goes in increments of 0.1 feet. Okay, so then after this point, it gives you the time and temperature data, and from there it's just plotting the temperature and versus time. But in this temperature, variable here, it's actually a matrix of all the different temperatures for all the different positions with respect to time. So if I go ahead and run this and didn't test this out before, so hopefully it does run. Okay, and it produced. Okay, yeah. So you see the workspace getting populated up. If I drag these windows back into the frame. Okay, so this is, we'll forget about this for now. This is to do with the nlinfit. This here is what you get out, or the way I have it coded up here with using the hold on function and plotting all the lines at one time. This is the type of information you can get after using ode45 and method of lines. You get this axis is versus time, okay, in seconds. This axis is your temperature in degrees Fahrenheit as I've written it, and this going down is increasing z position. So this would be z equals 0. Pretty obvious because it's at 250 and it's a straight line because it's always at that temperature. But as you can see, down here, this would be like the point z equals 0.1 feet, and so you can see that increases very quickly and then approaches steady state. The others down here, they don't approach nearly as high of a steady state temperature, and they approach that steady state slower, which is exactly what we expect. And so this is kind of the theoretical unsteady state startup temperature profile for the fin. And there will certainly be discrepancies between this and the experimental case. You should be thinking about what some of those are. The most obvious, I would think, would be that basically, as I have it here, this is like essentially a step response. You're given, like, you're saying at time 0 you're allowing heat conduction to occur through the fin. It's not nearly that neat or that precise in the experimental fin setup. It's not. What you're dealing with is not like an instantaneous, 250 degrees temperature of the steam at the base, and then all of a sudden it just starts conducting heat. It takes time for it to reach 250 degrees. So you'll definitely see discrepancies in this profile. So that's essentially ode45 for you. Now to think about the nlinfit. Basically, what nlinfit is. So ode45, of course, was it's numerically solving a differential equation. Nlinfit, on the other hand, is basically like a regression type function. So the neat thing about nlinfit is that you can define, if you know the form that of the equation that you want, you can specify that and then use adjustable parameters to determine the best fit. And so that's what I have down here at the bottom of the script, and this requires actually a lot less working than ode45 does, because all you need is, now going back to this experimental part, these again are kind of just guesses at what the experimental profile might look like. You'll have your own data, so you'll be importing it into MATLAB, probably using a UI import or something of that sort. At any rate, though, going back down here, for nlinfit, firstly you need a model. You need your model equation. So here's my model equation, and basically what I have here is I'm doing an at h which is my adjustable parameter, my heat transfer coefficient I'm going to be changing, and to try and make it best fit the data. And then this is the z vector here, and then this is basically your equation that it is the equation that I showed you previously, essentially, the analytic solution. So you write that out, and then all you do is you do it at your data points, which is your z and your temperature. So these are your data points that you collect experimentally, and you do it and you include your model, and you give a initial guess of h, the heat transfer coefficient, which I provide further up here in the code, as I just picked 20. It's kind of a guess, 20, but divided by this unit conversion because I'm doing it in English units. So now you can call nlinfit, and you can produce out all these different outputs. So there's like a total of 5 outputs here. You can do help nlinfit, and it will tell you what all these are. But basically, this is probably the main thing you're interested in. This is the prediction. This is the value of h that gives the best fit for the for that function for the data. And you can do stuff like get all this information out. This is residuals. So basically, just what's like if you take your model temperature, your predicted temperature, what's my predicted temperature minus my experimental, my data point temperature for all the different points. So you can get residuals out, you can get Jacobians, you can get covariances, all different types of stuff. So that gives me my experimental quote-unquote h that best fit the line. Then I can basically use that h from there, and using the same equation really as my model, plug that h back in. So no longer a guess, it's my regressed my regression h, and I can get the predicted temperature based on that h, and then from there it's just plotting. I'll bring that plot back into the picture. Yeah. So yeah, this is so the stars are, of course, would be our data points. Interesting thing to note here is that there's actually 3 things plotted on this graph, though you can't. It's hard to see them all. So the data points, or these points are experimental data, as I said. There's 2 lines in this plot, and because I have a large number of nodes right now, you can't see it. I'll decrease it in just a second. I can increase the size of this, and you should be able to see that there's like a solid line and a dashed line. The dashed line is the analytic solution. Okay, that's the dashed line is what we plugged in the h that we performed a regression on to get. Okay, the solid line is actually the method of lines thing from before. This solid line is the method of lines prediction for the steady state temperature, and as you can see, they're essentially on top of each other. Now what I can do is I can to demonstrate how changing the number of nodes affects the the accuracy of the method of lines approach, I can go back up here, and instead of doing 30 nodes, I'll be crazy and do something like 6 nodes. But in reality, you should be able to do much more than this, and eventually, if you put in enough nodes, you'll probably it will make your program run slow, but you should be able to do 100 nodes with no problem. We're not amateurs, so if you put in 6, then what happens is you get a lot more discrepancy in your method of line solution. It looks kind of raggedy because you only have 6 points, so you're basically like, this is 1 point and then this is the other point, so you're saying it's linear in between, and as you can see, the actual points that they predict aren't that far off from the analytic solution, but it's clearly not reflecting the nonlinear characteristic between those 2 points. So when you actually do the method of lines approach, you should be able to do, like I said, 50, 100 nodes, no problem. And so these are just some examples of analysis type methods, type ways to analyze this cooling fin. Not in any way the only two. You can look at fin efficiency. You can look at the total heat dissipation, which, by the way, those two are closely related. If you figure out the heat dissipation at different locations, then you can basically instantly know the fin efficiency, because it's defined as the heat it actually dissipates over the heat that the maximum heat it could dissipate if the entire fin were at the base temperature, in this case of 250 degrees Fahrenheit. So there's all types of different things you can look at, but these are just and really the other things that you can look at would be enabled after having done this, because you can, even though I didn't compute heat flux in here, you can find that pretty easily based on what I've done. So there's lots of different ways you can look at this, and but this is kind of some of the MATLAB intensive work that some of you might not have been exposed to. Some of you certainly have, but some of you might not have gotten to see as much of it. So hopefully this helps. Thanks.